Okay, ladies and gentlemen, we are happy to start our special session on Myanmar and we have arranged to have our colleague mostly from seismological side, as well as Dr. Ardalan in viewpoint of earthquake response. But Dr. Ardalan told me that he will be in the plane for an urgent trip and may not attend. Therefore, we will go ahead mostly with the focus on seismological aspects. I by myself and Professor Kayal, a prominent scientist from India, and my colleague Dr. Pourbeyranvand from IIEES will speak on the subject. Okay, I hope that Professor Kayal is actually in the meeting. I don't know, I'm not sure, but I am trying to see if he joined us or not yet. Okay. Professor Kayal, you are in the meeting. I will start. I am very happy to have you in our meeting. I will start my introductory notes on the Myanmar earthquake, and I will come back to you within about 20 minutes. Okay. Sagang Myanmar earthquake of 28th of March 2025 had a magnitude of 7.7, and it was really a major earthquake in South Asian region. The earthquake had, by the time being about 2 weeks after the earthquake, it had something around 400 aftershocks, magnitude 3 or above, and a fault rupture length of about 400 kilometers. And the important point to say was having damage in a distance of about 1,000 kilometers in Bangkok. It was a real, point, a real lesson to be learned from this earthquake. Myanmar, previously known as Burma by 1989, a colonial time name, actually have about 56 million population and a GDP estimation of 2024 of 68 billion US dollar. Therefore, you may imagine the size and the economic condition of this country in South Asia. As you may know, since 2020, early 2021, there has been a coup d'etat in that country. The military forces have been installed, and they are in power in the last 3 years. And the country has suffered specific instability due to political problems and unfortunately the earthquake has happened around 3,500 death toll is reporting from that city. The fault is strike slip. You may see from this cartoon images. Actually, the death toll, total death toll injured people and missing around 600 people still missing after 2 weeks from the mention. The earthquake occurred in a fault line between Indian plate and Eurasian plate. Sagaing fault is located in a north-south direction, and in the west of this fault zone, it is the Bay of Bengal, India, and okay. Let me. It's here. I will share. Okay, I will. Okay, I will put. I will put a sharing of slide. Let me. I will go through the screen. May you see? May you see the slide? Actually, okay, you may see it. Okay, and now is it visible? Still visible? Okay, that's okay. Okay, that's okay. Therefore, yeah, I was explaining that fault, north-south direction fault between Indian plate and Eurasian plate, and the earthquake evidently has covered a seismic gap, maybe something, a gap that, middle part of the fault segment in Mandalay has been ruptured. It was a previous earthquake in 1929, and another part, it was in 50s, it was another earthquake. Evidently, the part in between has been ruptured during this recent earthquake, 1956 earthquake. And the rupture surface is estimated to be 460 kilometer by 20 kilometer in depth, and it is mainly ruptured toward the south and about 75 kilometers toward the north. Therefore, you may imagine that the rupture propagation was mainly toward the south, and fault directivity might be observed in a north Bangkok and the other major cities locating in the south. Yes, the rupture duration time was something around 80 seconds. Therefore, you may imagine that the rupture duration was about 1.5 minutes. And displacement due to the fault rupturing was about 6 meters, as it was estimated by Geospatial Information Authority of Japan. And it is observed between 3 to 5 meters on the surface. Therefore, an estimation of something between 3 to 5 meters of observed displacement, and about 6 meters estimated during the Japanese association. Okay, if we think about the estimated values of intensities, as it is reported by USGS, you may see that the greatest values of intensities are observed along the fault, and there are some specific points of higher damages around Bangkok. The colors are estimated intensities, instrumental intensities, and the points mentioned by small circles are reported earthquake intensities. The Sagaing earthquake of magnitude 7.7 is occurred about 14 kilometers north of Sagaing. It was very close to the cities of Sagaing, a small city of Sagaing, and very especially to the city of Mandalay, about 20 kilometers. It was very important. And as I have mentioned, about 1,000 kilometers to Bangkok. If you observe the peak acceleration, values around the epicenter and within the distance of about 1,000 kilometers, you may see that the attenuation of intensities are mostly in accordance with the attenuation models, but there have been some specific locations having greater than predicted intensities. Why, we may explain in the future, but I may insist that the higher intensities correspond to site amplification and rupture directivity. I mean, super shear propagation of rupture caused a slash type of pulse, and especially in the fault normal direction, and it caused in a city such as Bangkok, where there are tall and high-rise buildings, we may observe that the damages has been important. As I told you, a 33-story tower collapsed. An amplification of about 0.1 to 0.2% of G, evidently due to amplification, soil amplification, was higher than predicted, and this 33-story building has caused about more than 70 death toll, and the workers who were working, because the earthquake has occurred during the day, but it was around early afternoon. Therefore, the people have been working in the building, and it caused the death toll. And on the other hand, we may mention that the earthquake caused by, the amplification of the waves has been caused by soil amplification, and in some cases, the ground deformation caused by liquefaction has been the reason for damages, local damages in Bangkok. This is the building which has been collapsed, a 33-story building which have collapsed, and a PGA of 0.62 G, about 200 kilometers to the epicenter, has been recorded in a station installed by USGS. Evidently, we couldn't find very close to the epicenter location. And we may say that if there have been more strong motion station around the epicenter, it could be a source of studying of ground motion, especially for the near field. But by the time being, the closest distance, a strong motion station was about 190 kilometers to the epicenter in the city of Naypyidaw, if I am pronouncing right, the capital of Myanmar. the ground velocity was 161 centimeter per second, and as you see, even in the distance of about 200 kilometers, the peak acceleration was effectively very high. It was toward the south of the epicenter. Therefore, we may imagine that even toward the south, in a distance of 200 kilometers to the epicenter, it was great pulses causing the damages. Why that 33-story building has collapsed during the earthquake? It was due to the long period resonance of high-rise building. It was due to the higher PGA observed and occurred due to the site amplification, due to the vulnerability of the buildings, and effectively in the wave propagation could sustain an intensity of about 5-6 in the very far distances, and the material used in the building are estimated to be substandard. Therefore, for instance, the substandard steel have been used in that building in Bangkok. Therefore, by the time being, we may say that the event had long period energy, significant long period energy. The long period wave, due to the long period wavelength, caused important damages even in the far distances. High-rise building have suffered very important swaying, about 50 centimeter to 100 centimeter swaying effect in 1,000 kilometer distance, and sloshing liquid had about only about 0.5% of critical damping, but the condition in the roof of tall building was not suitable to sustain because of this sloshing liquid. Therefore, this was an introduction, a very brief introduction I wanted to represent. And if there is any comment, I am at your service. And meanwhile, I ask Professor Kayal. Professor Kayal, are you online? I see that you are there.
Yeah. I'm there. Yeah. So should I start?
Okay, Professor Kayal, thank you very much to accept our invitation, and you may share your PowerPoint, and we are ready to hear you.
Okay, thank you so much, Dr. Zare. Thank you so much. Let me see if I can share. It should work. Please allow me to share. Please allow me to share my slides.
Professor Kayal, we may.
Yes, I'm trying to share, but it is not coming from your.
I think that.
Can you hear me?
Yeah, we have your voice.
Yeah, but for sharing,
oh no, sorry. Okay.
Yeah.
Have you shared your PowerPoint?
No, I could not yet, but because I have already clicked the share, the required window is not coming yet.
Okay, I may ask maybe from Dr. Pourbeyranvand to go ahead, and you will have the time to join your PowerPoint. Dr. Sharaf, you have your PowerPoint? Yes.
I don't know what is happening. Can you see the PowerPoint? Can you see my PowerPoint?
Not yet.
That means that permission is not coming from your admin.
Permission? Why? من چیکار کردم؟ من که خاموش کردم. You may send, Professor Kayal, you may send your PowerPoint using email or WhatsApp. I will share it here.
Okay, that will take some time.
No, you may make a PDF of your PowerPoint and then send it by email to me.
No, I can send it. But the point is, why it is not coming? The share I have clicked, but nothing is coming. Have I joined? I think you can hear me. You can see me also. Can you see me?
Yes, we are seeing you.
And you can hear me, but why sharing is not coming?
Share a screen.
Yes, I have clicked the share, and then that window should come. That window has not yet come. Why?
But I think that it is easier that you send it. I mean, you may make a PDF of your.
It has come now.
Okay.
So I think now I can share. Now can you see my slide?
Okay. Yeah.
Okay. Thank you, Professor Zare, for your kind introduction on this particular aspect of March 28, the Myanmar aspect. And I will try to just give you a glimpse of the few observations, the seismological observations that we have made for this aspect. So let me go I think this is all known that our seismology is very far, only 125 years or so. From analog to digital, we have come in the 1990s, and our data is digital data is only about 25, 30 years. So seismological data, instrumental data is about 100, 130 years. We are getting, and based on this, we can define the boundaries based on this observation. And I will just take you to this slide. And in India, we started these observatories from 1899, say 1898, after the 1897 Great Long earthquake in northeastern India. Then after the Kangra earthquake and 1905, some more stations. And after the 1993 Kayal earthquake, we have started digital networks since 1996. And today we have something like 200 observatories and some 500, clusters network. So I think this is the basic things that how we could locate the earthquakes before computational technique came up. That is to be located manually, then by computational techniques since 1960s, by least square method, then by different precise method have come up like joint hypocenter, double difference, and seismic tomography. And we can locate earthquakes very precisely by this seismic tomography or simultaneous immersion of data, and we can also image the earth structure by tomography. So this is our all young science, and we have just started this say since 1970s, 80s with the good data set. And this is how we try to understand the earthquake focal mechanism based on elastic rebound theories. And we can, based on the earthquake POA fast motion, we can try to understand this mechanism, or based on the nowadays with the digital data, based on the waveform inversion, we can also come out with the fault point solutions. These are the beach balls that we present for different types of mechanism of earthquakes, like thrust faulting, normal faulting, and strike slip faulting. And sometimes they're complicated with no strike slip component of normal faulting or thrust faulting. Now, this is where we have come to some, understanding of the plate tectonics in the Indian plate movement. As you all know, the Indian plate some 70 million years ago, this was here, and today the Indian plate is here with head-on collision with the Eurasian plate over here. And if you see in this map, you find that the Indian continental part of the plate, which is coming from the Kazakh Greece somewhere here, it is moving to the north, and the oceanic part of the Indian plate is subducting below Andaman Sumatra Trench subduction zone, and this is connected to the Indo-Burma ranges over here, which is also a atypical subduction zone. This is a continent situation, but still the Indian plate is subducted. Indian plate is very well, observed. So this is the collision zone in Himalaya, how the Indian plate and the Eurasian plate on collision and Himalaya has come up. And this is the subduction tectonics along the Andaman Sumatra subduction zone. The Indian plate is going down, and all along this island arc we are getting volcano and the deep earthquakes. If you come to this map, you can see that all along the Himalaya, we have got intense seismicity, and also in the Indo-Burma ranges, intense seismicity, which is connected with the Andaman Sumatra subducted zone. So if you look at the section of the earthquakes, you will see that below in the Burma ranges, the earthquake is going down to 200 kilometers depth. Below Andaman, something like 300, 350. Below Sumatra, about 400. And below Java, the dipping seismic zone down to 660 kilometers. So this is what is the Indian plate, on head-on collision in the Himalaya, shallow earthquakes in the Himalaya, and with the subduction tectonics in the eastern part, we are getting deeper and deeper earthquakes, and thereby subduction processes. Now, if we come to this recent large earthquakes in the Indian plate, we find that there are a lot of large and some great earthquakes from the star symbols, and the large earthquakes are by circles. Large means more than 7 and above, and great means 8 and above. And in the inter-state region of India also, there are some earthquakes which are magnitude 6.5, but in the western part of India, you can see there are large earthquakes and great earthquakes too. But if you come to this part of the country, northeast India and Midland, where in the Burma ranges and Sagai Fault, I think more than 16 or 17 earthquakes during last 100 years that has occurred over there. And these are the two largest earthquakes that we have experienced recently, that is magnitude 7.7, the most devastating earthquakes in the Sagai Fault, and that magnitude 9.1 or 9.2 in the Sumatra subduction zone. So this is that seismic belt, in the Burma subduction zone, which is connected, a typical subduction zone, which is connected with the oceanic subduction zone over here, and this is the Himalayan, collision zone. So this is a very, very complicated tectonics in Southeast Asia, and we have some seismic images of the subducted Indian plate below in the Burma region, and that shows that this is in the Burma ranges and a cross section across the Burma ranges and Sri Lanka too. We find that the subducted Indian plate is actually down to something like 400 kilometers, still there, but the upper part of the plate is now seismically active, whereas the lower part of the plate may be torn off or is not seismically active. This is fitting very well with this plate tectonic model. We get earthquakes for the subducted shallower part, and for the subducted deeper part we get thrust faulting, and this is also giving much deeper depth. And here the upper part is seismically active, and the torn off part may be active or may not be active. That is what is may be active is some sort of model is also found in Java ranges. The deeper part of the subducted torn off plate is not seismically active. So this can be the different model can be obtained, and I think below in the Burma ranges, this model fits well. That upper part is now seismically active, and the lower part is no more active. And this is our more detailed investigation. This was done by Kayal, and in joint project we also joined him to understand the subduction structure below in the Burma ranges. Now, with the recent seismicity, we try to understand the seismotectonics of Northeast India region and in the Burma ranges and along the Sagai Fault. As you all know, that there is a great earthquake in the syntactic zone where the Indo-Burma ranges and the Himalayan collision zone are meeting. At this syntactic zone, there was a great earthquake in 1950, great earthquake by seismic mechanism. And then all along the Indo-Burma ranges, there are large earthquakes, and all along this Sagai Fault. This is Sagai Fault. This is Myanmar silver plate, and this is Sanda plate or Eurasian plate, and this is Indian plate. So all along this tectonic zone, this is subduction zone, and this precisely faulting zone over here. And if you see the sections, along the Himalayan belt in the northeast Himalaya, you can see the earthquakes are mostly within 50 kilometer depth. But as you come to across this Sri Lanka too and in the Burma ranges, you can see that there is a clear subduction zone down to 200 kilometers. Further across Bengal Basin and in the Burma ranges, the earthquakes are down to something like 200 kilometers. And this section is showing along the subduction, along the Indo-Burma ranges, you can see that earthquakes are deeper down to 200 kilometer or 180 kilometer all along the strike, strike direction. But beyond 26 degree latitude, the earthquakes are following. That means no more subduction tectonics is there beyond 26 degree latitude from somewhere here. So there is a creaking of the saline fault in this zone, and this saline fault which is not almost not south direction. That part is seismically much active. So, and another observation we made, whether it could be, we can term it as precursors, that was this part of the saline fault where the main shock occurred in 2025. This part of this zone was found to be quite very much strained by GPS survey. This is done by USGS, and this map I taken from there. And most recently, we have also observed some, some swarm type of activity in the Burma, in Mizoram area, in the Burma ranges. There are some, in that region, there are something like every 5 years we have tried to plot these earthquakes, 5 and above. And we have seen the average activity of magnitude 5 and above was of the order of 5 or 6. All from 1965, we have taken this data. It was average 5 to 6 earthquakes, 6 to 7 earthquakes, magnitude 5 every 5 years. But between 2015 and 2020, the activity was of the order of 20 earthquakes, magnitude 5 and above. And there was a swarm. This swarm we have tried to check in the model. We found that this has all these earthquakes, something like 8 or 10 events of magnitude 5 and above occurred within 8 months, and that occurred in the the Burma River, and this is the saline fault over here, and the 25 earthquake occurred at shallow depth on this saline fault. So whether it could be a precursor, I don't know, but this is our observation, and we have to make some more detailed study about this observation. And then, as already Professor Zare has already explained these features, that there are some observations that several earthquakes, more than 7, occurred on the saline fault in the 1990s. Several earthquakes, and the part of the gap between 1930, actually, Professor Zare also told 1929, but it is in the USGS that I find is 1930 and 1956. The 1930 earthquakes were over here. If you can see in the south, this is 7.2 or so. If you can see my arrow, this is 1930 earthquake ruptured zone, and this is 1956 earthquake, 1956 7.5 or so. This is the ruptured zone. And there are several earthquakes in 1990s, 7.6, 7.3, 7.7, 7.3, like that. There are some couple of earthquakes which ruptured the northern part of the saline fault and southern part of the saline fault. And the gap between 1930 and 1956, this is the 1957, 7.2 or 7.1. So these ruptures and these ruptures in south, there was a gap in between. So now this gap area is ruptured by this 2025, mega or large earthquake 7.7. And GPS study, of course, I have already mentioned some strain, and they were expecting some rupture anytime in 2000s. And this is function because they have estimated the ground system at the epicenter region could be more than 1 G. That was observed for an earthquake in Sri Lanka to over here, 1950, 1897 earthquake over here. 1950 was here, and 1897 was here. And Oldham, that time there was no strong motion instruments, but Oldham, the geologist, he estimated the G value could be of the order of 1 G, ground acceleration of the order of 1 G, because boulders were thrown. So if it's more than 1 G, the boulders will be thrown in the sky. That's what possibly is observation for this earthquake at the epicenter area. I am not sure, but recorded PGA 200 meters away, as Professor Kayal mentioned, about 200 meters away, the recorded PGA is of the order of 0.62 or so. And as he has mentioned that, the aftershocks all started going to, to the south of this fault, and there are some 300 aftershocks within a week or so, and the rupture propagated for south, as already mentioned by Professor Zare. So this is what happened, and I can just give you one more example of such thing happened. This is also shown by Professor Zare that the maximum intensity was of the order of 10 maximum intensity in this zone, and this is the maximum intensity zone, and then from 6 to 8. A map is shown over here. Now, the Bangkok is here, which is maybe in the zone of 5 or 6. Bangkok maybe about 1,000 kilometers, 800 kilometers away from the maximum zone, maximum intensity zone, and that high-rise building collapsed. And I think it is well explained by Professor Zare. I need not to again repeat it. I just want to show you another example of Bhuj earthquake. This was in the western part of India. That 7.7 earthquake at the depth of 25 kilometers. The maximum intensity was of the order of 10, and this is 9. And Ahmedabad city was over here, which was in a zone of 6 or 7, and that many multi-story buildings, they just sank into the ground due to liquefaction of water. So such thing is not surprising when building frequency resonates with the low frequency seismic waves. So that is what has happened also in Bhuj, and that's what also happened in Bangkok. This is site characteristics, the building material, and natural frequency of the building and the grounds amplification frequency. If it matches, the structure collapses. So these are the regions we can we can think of for such disaster of the multi-story building in Bangkok, how it collapsed. Now, if you permit me, I can give you another 5-10 minutes presentation. That is what is our, now these are the things we are only observing, but what we can do about the earthquake disaster mitigation. I think earthquake prediction, and the answer is no. Till today, I will not go into detail about the high chain earthquake prediction or some forecast in the Myanmar ranges in 1986, but they have had no practical implications except the 1975 high chain earthquake, but that's a different story with animal behavior and all. So let us say that earthquake prediction till today, we cannot predict earthquakes with time, space, and magnitude. But we can identify the earthquake source zone, earthquake fault zone. We can do the seismic hazard microdiscrimination map for making for urban development, for making earthquake resilient buildings. We can also do something with the tsunami warning or earthquake warning. Earthquake warning has no practical implication for the society. This for only emergency service. But earthquake tsunami, I think we can do this and we can save life. But earthquake prediction as of today, with time, space, and management, we can't do that. Now, for seismic hazard microdiscrimination, there are different approaches and multidisciplinary approaches, like seismological investigation, geophysical investigation for bedrock configuration, geological investigation for active faults and sediment thickness, geotechnical investigation for liquefaction factor and other things. So these studies are, in detail can be studied for any engineering construction and for any urban development, and the map should be properly used for making a resilient society. You see, this was the fate of the Chichi earthquake, that dam failed because the river itself was a fault, and in those days, it's old dam, and it was not, I think, properly detailed investigation was made to find out the active fault over there. And on the active fault, this dam totally held by the 1960 earthquake. This is also what happened in Bhuj. A well-built structure totally, collapsed due to, it was standing on fault. And similarly for the Kashmir 2025 earthquake, how the multi-story building totally is damaged. So these are the, some active fault can totally destroy any structure. And now the comes about side response. We all know about side response, that we talk about. Now, if a structure with same design, same material standing on a basement on hard rock, the seismic waves, when it comes from this source zone, it is coming like this and the structure will stand. But when this same seismic waves from the same earthquake is coming and passing through this sediment, and this earthquake amplification is highly amplified in the sediment zone, and that damages the structure. Same material, same design. So that is called side response. If your structure is on the loose down and not properly designed, that will collapse. That's what happened for the Bangkok structure. This is experimentally. We can also, we have recorded that how on different lithology, the earthquake, from a magnitude 4 earthquake, the seismogram was studied. For the hard earthquake, the seismic waves was this much amplification, but for the Holocene mark, very, very loose material, it was highly amplified, and for the quaternary alluvium, it was medium. So the seismic waves, same seismic waves, it gets amplified in a loose soil, and that is what is particularly for the landfill areas where the big structure comes. These things should be taken care of. The seismic waves can be amplified and the building can collapse. This is what we first time we did it from Geological Survey of India. We tried to start the Jabalpur area in the middle of in the center of the Indian, peninsular India. The Jabalpur earthquake was here, and that destroyed a lot of buildings here. And we found there are discrepancies. Some buildings are standing, some buildings totally collapsed. So we made a pilot project and studied the different soil characteristics, very close spacings, and we found that there can be height amplification, and that amplification and frequency. So if your frequency matches with the building frequency at which the seismic waves amplified, your building totally collapsed. And we come out with this seismic, hazard map, and then the risk map, depending on the urban, development. We have tried to see what are the area which will be at a very much risk. People are living there in a multi-story building. This is another study, that the multidisciplinary study for migration in Guwahati city. That is, as you can see, this is the northeast part of India, which is the highest seismic zone, zone 5, means average G value is 0.4, and this is also western part of India, as I said, Bhuj area. These are the two zones which are zone 5, and some patches of Himalaya are zone 5, then zone 4 and zone 3 and things like that. So Guwahati city is somewhere here, over here in northeast India, in Assam Valley, and you can see the Guwahati city, the seismic migration map we have made based on several geophysical, geological, seismological studies, and you can see that this is the hazard migration map, and this is the land use, where are the buildings and how many people are living. All these things are brought to GIS platform, and we have come out with this seismic risk map. So these are the spotted, the red spot are seismically very highly risk. Any large earthquake occurs, I think the immediate the rescue parties would go there, and these areas, any construction, should be seismically designed. So that is what the map is. Scientists can give you the basic data and the map, and it is engineers who has to build the house to make a earth resilient society. You can see that in Japan, what happened, this is, after Kobe earthquake, every building, after built before 1980, this is ERI building, after Research Institute in University of Tokyo. This is the old building and this is the new building. And just face to face, the old building before 1980 are all retrofitted. And the all new buildings, any building after 1980 are made with seismic design. So this is how Japan takes lesson. And this is the Kobe earthquake, museum. This is the actual spot where a textbook type of reverse faulting. You can see the ground has gone up with a dipping fault. So this is now kept as a museum for the future generation to see how this earthquake occurred. And now, but they take lessons like this. And in Bhuj city, it was totally destroyed, and the new Bhuj city has come up. But I think I'm not sure whether really they have taken care of the seismic hazard maps to make up this, to build this new city. I think I'll just touch upon another part of disaster, natural disaster in India and Southeast Asia. That is due to subduction tectonics. We get earthquakes in the seafloor, and so our tsunami source zone is Sumatra subduction zone, Andaman Sumatra subduction zone, another zone over here, Makran subduction zone, and these are some mega earthquake occurred. Mega means 9 and above. They occurred in the subduction zone. They all cause disaster with tsunami as well as with the ground shaking. So this is, you can see how the that mega earthquake, Sumatra earthquake. This is the epicenter of the mega earthquake. How rupture propagated along to the north, and it has reached up to 1,500 kilometers up to Andaman Island. And in Andaman Island, in Port Blair, a tree was split by this, and separated, and they are also separated by for a few meters. So this is how a mega earthquake, rupture zone propagates, and it causes such a thing about 1,500 kilometers away. And this activated the Mars volcano. This destroyed the one military base, air base here, the liquefaction. So this is what is what is our another Indian plate subduction zone here causes tsunami sources are there, and this is how the tsunami reaches to the Indian coast and Sri Lanka over here. How the earthquakes in this subduction zone, and we are of course much little better off in a sense that it takes about 2 to 3 hours. And by that time, we had no tsunami warning system before 2004. Now, after this earthquake, we have tsunami warning system, and we have, and this was the damaged coastal part of the country totally affected by the tsunami. So, and a lot of casualties also occur in Indian East Coast region and also in Sri Lanka. But now we have got the tsunami warning system. This is the tsunami warning system. Now it's working in Hyderabad, and they are doing a good job. Now we have got coastal observatories and the ocean bottom seismograph, and on real time they are recording, and they are doing good job. And any earthquake more than 8 and on the seafloor, and by thrust faulting, it causes tsunami, and this can be handled. Tsunami warning can be given, and lives can be saved. Now they have also have done something the early warning system in the Himalaya in Uttarakhand, and it is successfully now in operation. And they can give suppose the earthquake has come, immediately they can know that earthquake magnitude, and it may take some 30 to 40 seconds if the earthquake is at a distance of 300 to 400 kilometers. So that period, 30 seconds or 35 seconds, that gap is there before the shear wave, which comes and destroys the structures. So during the short period, I don't think multi-story building can be evacuated. I think it is only made for emergency service, like stoppage of the bullet train or nuclear power plant and so on. Emergency service can be immediately stopped. But they are giving warning, and people can on the car they can stop and they can be quiet and all. So some little importance is there so far the practical application is concerned for the life of the human being, but they are useful for the emergency service. I think these warning systems are okay, but we should learn to live with the nature. I think our houses, our cities should be developed with a proper seismic design, and we should learn to live with the nature. Thank you very much for your kind questions listening. Thank you all.
Thank you, Professor Kayal. Very interesting presentation. Professor Kayal is a well-known scientist in South Asia for his works on seismotectonic and seismology of Indian Peninsula, not only on India, but also for surrounding region. Therefore, he has a book published, I think in 2020, in Springer, if I am right, on the seismotectonic of Indian Peninsula earthquake, and several articles published in BSSA and other prestigious journals of seismology, who all represent the vast domain of researches of Professor Kayal. Thank you very much again. I hope that you will stay in the session, and we will. Okay, we will go to listen. Dr. Shahrukh Pourbeyranvand, are you ready? Okay, you will come here. Okay, please. Professor Kayal, you will stop sharing. ما میتونیم این پست کنیم دیگه. چرا؟ شون باید استاپ شده کنه. خودش باید بزنه. Professor Kayal. یا من باید. استاپ. اگر هنوز نکرده بس. اوکی. حالا بزن.
Okay, thank you very much for the time. Do you see my slide? I would be thankful if someone answered.
Check. No.
I guess it should be shown on the screen.
You go to view. Go to view, is that? Well, here, create view.
Create view.
Okay, they are saying that they see the presentation.
Okay.
You may go ahead. Okay, that's okay. Go. They are saying that that's okay.
Okay. Thank you very much. I would like to thank my colleagues for organizing this meeting and the time spent to my talk. My talk is about the preliminary report of the Myanmar earthquake. I benefited from the collaboration of some of our colleagues, Dr. Javan, and also two of our graduate students, Amir Hossein Firouzian and Human Salimzadeh. I should skip some of the contents of my presentation because my colleagues thoroughly discussed the earthquake and its characteristics, its magnitude, and the great impact on the surrounding areas, which is about 1,500 kilometers, and the huge amount of damage which is caused by this earthquake, as we will discuss in the next slides. It is because of the super shear characteristics of this earthquake. In this poster, the general information about the earthquake from USGS is mentioned, the focal mechanisms of the events, including the main event with 7.7 magnitude, which is a right lateral strike slip event, and its greatest aftershock with 6.4 magnitude, and other aftershocks which are shown on the slide. And this is the waveforms recorded at INSN, the broadband seismic network of IIEES, which shows the waveforms in our stations and some of the international stations that we have access to. This is the shake map, shake intensity, and also the USGS map of the events. I skipped these slides because they are discussed before. And this is a interesting GIF image of the massive 500-kilometer long land rupture, which is captured by satellite images. Of course, these kind of displacements can be seen even on Google Earth, but because of the short time period since the earthquake, it is not accessible right now on Google Earth. The tectonic background of the area is also discussed, so I skip this slide, and you can see the Indian plate history through geological time from 71 million years ago until today. It is going toward Eurasian plate, and in these slides I tried to show the significance of Sagaing fault, which accommodates some of the movement in strike slip form. This earthquake and its study area is especially of importance to us because of the similarity between our tectonic setting and Himalayan tectonic setting. As discussed in a paper in 2010 by Hatzfeld and Molnar, there is a interesting similarity between the Zagros and the Tibet or Himalaya. You can see in the image on lower left part of the slide that the movement of Arabian plate toward Eurasia is quite similar to the movement of Indian plate toward Eurasia. What happened in Myanmar could potentially happen in Iran. Of course, there are differences between these two tectonic setting environments, and the intensity of the earthquake is greater than what expected in Iran, but the similarity is of interest to us. As discussed in previous talks, the significant Sagaing fault in the area is shown on the map, and also the tectonic environment, the focal mechanisms of the earthquakes are shown, and also the Indian plate and the Burma microplate in the middle, and the Sonda plate on the right side of the central image. You can see the subduction procedure in this slide. Here another image of the Sagaing fault, and on the schematic view, it can be seen that the movement of Indian plate toward Eurasia in upper right of the slide, it can be seen that about 20 millimeters per year is accommodated by Sagaing fault in form of a strike slip, and the oblique slip is accommodated by other faults as mentioned in the slide, and totally 35 millimeter per year is the movement. Okay, thank you. Is the total movement between these tectonic plates. And in this slide, the subduction is illustrated. You see the Indian plate, which is subducting beneath the adjacent plate, and the Burma microplate is occurring between these plates, between Sonda plate and Indian plate. I mentioned the super shear property of the earthquake. There has been a lot of recent studies on super shear earthquakes because of the huge damage which can be caused by these earthquakes. Super shear phenomenon is explained in this way. When the earthquake is a super shear event, then the rupture speed exceeds the shear wave velocity. This contributed to intense ground motion and significant damage even in distant locations like Bangkok. So the demolishing of the skyscrapers in Thailand and far areas is due to the super shear property of this earthquake. I wanted to demonstrate آره میخوام اینو ببینم که پلیش کنم.
اونجاست بغلش
اینه؟ ها اینه. Okay. Yes, sorry for the time. I wanted to show this presentation to show the super shear property as simple as possible. You know, that's this professional skateboarder is trying to come down from this mountain at this point, yes. You see that the speed of the skateboarder exceeds the speed of the avalanche. This is the same as what happened in a super shear earthquake. Of course, this is not only a demonstration, it is supported by a scientific study, and it is published in a scientific paper. And a slab actually here is similar to the slab in the geological context, and the force by the skateboarder is similar to the force by the earthquake. And this is also a view of demolishment of a religious monument of Buddha. Unfortunately, it is devastated. We go forward to radar interferometry studies, which is conducted very rapidly after the earthquake. You can see the fringes and the displacement maps. Of course, because of the high amount of displacement and movement along the fault, very near field areas are subjected to noise from interferometry point of view. Here, the coherence, if you can see the, okay. In the left side, the coherence image can be seen that shows the coherence is quite low in the area because of the high deformation occurred by the earthquake co-seismically. In the middle, the optic image of the area and some cross sections can be seen, which shows the displacement. And at the right side, this is the INSAR study conducted by one of our students, Human Salimzadeh. He intentionally made the image in black and white to show high noise in the deformation zone. And here is another result of his work, which is the interferogram as a KMZ file overlaid on the Google Earth, and this is the unwrapped image, which has better quality. Another approach in remote sensing nowadays is pixel offset tracking, or POT, which has higher accuracy for measurement of the displacement, which is shown here. And you can see that according to the scale from 2 to -2 meter, it is about 4 or 5 meter of displacement. And also Coulomb stress study has been conducted on this earthquake. The earthquake increased Coulomb stress along adjacent fault segments, heightening the risk of future seismic events in the region. And in case of aftershock, a significant aftershock magnitude 6.4 occurred just 11 minutes post-earthquake, emphasizing ongoing seismic activity. Okay, and another part of our study is about the precursors of the earthquake. The concept of anomaly detection from a time series of registered parameters is discussed in this slide. As we all are familiar with this kind of studies, when we are studying a parameter, special parameter, for example, like geomagnetic field, we should consider the uncertainty of that quantity. In this figure, the orange lines are the limits of the uncertainty of the purple line in the middle, which is, for example, which can be any parameter like geomagnetic value. And it is important to note that any anomaly should be outside the uncertainty of the parameter. For example, in cases 1, 2, and 3, these are local maximum or minimums, but they are not considered as anomalies because they fall into the interval of the uncertainty of the data. But the true anomaly is shown by the red arrow on the middle. We followed this approach, and you can see the so-called characteristic curves of the geomagnetic data, which we conducted through several years for many different case studies. These characteristic curves can be different due to the site properties, geological properties of the observation site, and also it depends to the component of the geomagnetic field that we are studying. For example, it can be HDZ or XYZ or etc. We implemented this method by help of our colleague and our graduate student, Amir Hossein Firzian, who did a very good work on this issue, and he implemented this approach on swarm satellite magnetic data, and we can see here that the uncertainty band of the magnetic data in the slides. One single anomalous data is observed in the left side, which we believe it can be the earthquake precursor. And the map of the area is also shown on the right. This is related to Myanmar earthquakes. As we know, the Myanmar earthquake happened on 28th on March, and this anomaly occurred about 20 days before the earthquake. And these are very interesting images, show different components of the geomagnetic data recorded by swarm satellite. In the upper image, the left one is the north direction, the middle one is the east direction, and the last one is the central component, which is toward the center of the satellite. And in the lower diagram, the color indicates the distance, the time distance between the occurrence of the earthquake and the time of the recording. These images also can be shown interactively. I hope, unfortunately, it cannot be shown here, but Amir Hossein did a very great job to make these figures interactive. You can, as it can be seen here, if I could have the opportunity to show it to you, when you move the mouse of the computer on these figures, you can see the dates and the value of the components, and this is very helpful to analyze the data of searching for possible precursors of the earthquakes. And also we studied the geomagnetic storms, because many times it coincides to the earthquake precursors. In the left diagram, the blue point on the upper right is the time